Okay, this video is going to be on section 4.6. We're going to be looking at directional derivatives and gradients. So for the directional derivative, let's suppose you want to travel a certain direction from a point on the graph of z is equal to f of xy. So point on the graph. The point being z equals f of ab for some a comma b in the domain of f. Let theta be the angle from a comma 0 in the direction chosen from the positive x-axis in a counterclockwise motion. If we travel a distance of h on the xy plane in the chosen direction, we arrive at the point a plus h cosine theta, comma b plus h sine of theta. On the surface, this point is z is equal to f of a plus h cosine theta, comma b plus h sine of theta. So we'd walk a certain distance, and then we're going to find the slope of this secant line here. Finding the slope of this secant line between these 2 points, m is equal to f of a plus h cosine of theta, comma b plus h sine of theta, minus f of ab all over h. And so that's going to measure how much we go up or down with respect to z. So if we walk a certain direction, do we expect to go up a certain elevation or down a certain elevation? Given a function of 2 variables, z is equal to f of xy and ab in the domain of f of xy, then the directional derivative of z equals f of xy in the direction of the unit vector cosine theta I plus sine theta j is, and so this is the notation, so the directional derivative of f of ab in the direction of u is equal to the limit as h goes to 0 of f of a plus h cosine theta, comma b plus h sine of theta, minus f of a, comma b all over h, and then of course provided this limit exists. Okay, so that's all being described here on our surface here. And you can see this on page 426 in the OpenStax book. Okay. All right, let's go on to the next slide and we'll look at a theorem. Oops, too far. So we'll look at a theorem for the directional derivative. If z is equal to f of xy is a differentiable function of x and y, then the directional derivative of f in the direction of the unit vector u, which is equal to cosine theta I plus sine of theta j, is the directional derivative of f of xy in the direction of u is equal to the partial derivative of f with respect to x, cosine theta, plus the partial derivative with respect to y of f times sine of theta. Note, this is not a vector. This is going to be a scalar. So if it's positive, we can say that we're going up if we pick a certain direction, and if it's negative, we're going down. If it's 0, then we're going to be on a level surface, a flat surface. Okay, so the idea of the proof here is the directional derivative of f of ab in the direction of u by definition is equal to the limit as h goes to 0 of f of a plus h cosine theta, comma b plus h sine of theta minus f of ab all over h. So if we put x is equal to a plus h cosine theta and y is equal to b plus h sine of theta, we can define a function g of h, which is equal to f of xy. Since both the partial with respect to x and partial with respect to y of f exist, we can apply the chain rule and take the derivative of g of h. So g prime of h is going to be the partial derivative of f with respect to x, dx dh, plus the partial derivative of f with respect to y, dy dh. So partial derivative of f with respect to x is going to be just other notation, and then the dx dh and dy dh are going to be cosine theta and sine theta respectively when we take the derivatives of both the x and the y with respect to h. The a and the b are constants. Okay. All right. Now if we evaluate this at 0, so g prime of 0, so if we're at h is 0, then that knocks off these two guys, and so y is equal to a, and x is equal to a and y is equal to b. So g prime of 0 would be partial of f with respect to x ab of ab cosine theta plus partial of partial of f with respect to y of ab, and then times the sine of theta. So g prime of 0 by definition is equal to the limit as h goes to 0 of g of h minus g of 0 all over h, and this is equal to the directional derivative of f of ab in the direction of u, and so this gives us the formula for the calculating the directional derivative. Okay, so let's do a couple of examples of finding the directional derivative. Okay, so example number 1, we're going to find the directional derivative of f of xy is equal to x e to the y, and then we're going to go in the direction of theta is equal to 2 pi over 3. Okay. So directional derivative is going to be partial derivative of f with respect to x evaluated at xy cosine of theta plus partial derivative of f with respect to y at xy sine of theta. So partial derivative of f with respect to x is going to be e to the y. Partial derivative of f with respect to y is going to be x e to the y. Okay, so we can go ahead and plug that in, and also plug in 2 pi over 3 for theta. So it's going to give us e to the y times negative 1/2 plus x times square root of 3 over 2, or it'd be 1/2 e to the y plus, 1/2 e to the y times the quantity square root of x, I can't say it, 1/2 e to the y times the quantity x root 3 minus 1. And so then we would just pick a xy pair in the domain, which is going to be all possibilities for both the x and the y. It's going to be all real numbers for x and y. That'll give us a z value, and so we'd be standing on the surface at a z value, and then if we wanted to go in the direction of 2 pi over 3, this would tell us what the rate of change would be at that particular point. Would we expect to go up, down, or would it be level? Okay. Let's do another example here, and this one will have a little bit more concrete. We won't just have a generic directional derivative. This one is example 2, so we're going to find the directional derivative of f of xy, which is equal to x squared minus 4xy, and the point is 1, 2, and we're going to go in the direction of the vector 4i minus 3j. So 4i minus 3j is going to be a vector in quadrant 4. We'll use the Pythagorean theorem to find the hypotenuse Okay, so this is going to be a 3, 4, 5 right triangle, so the hypotenuse is going to be 5. Okay, and we need to, in our directional derivative formula, we need to know the sine of theta and the cosine of theta. 4i minus 3j is not a unit vector. It does need to be a unit vector, or we can approach it this way. And the sine of theta is going to be negative 3/5, and the cosine of theta is going to be 4/5. Okay. The partial derivative of f of x, y with respect to x is going to be 2x minus 4y, and the partial derivative of f of x, y with respect to y is going to be negative 4x. Okay. So our directional derivative of f of x, y in the direction of the vector u is going to be 2x minus 4y, and then the cosine of theta is 4/5 plus a negative 4x, and then the sine of theta would be negative 3/5. Okay, and so what we need to do is evaluate this. They give us the point 1, 2, so we'll go ahead and evaluate that. So we have 2 times 1 minus 4 times 2 times the quantity 4/5, and then plus, well, I guess I didn't absorb the negatives yet, so negative 4 times 1 times negative 3/5. Okay, so it's going to give us negative 24 over 5, and then plus 12 over 5. And so that's going to give us negative 12 over 5. Okay, so if we're standing at the point 1, 2 on the xy plane, then the z-coordinate would be, let's see, that'd be 1 squared minus 4 times 1 times 2. So that'd be at negative 7. So it'd be at the point 1, 2, and negative 7. And if we decided to go in the direction of 4i minus 3j, then our rate of change in the z would be negative 12/5. So that would say if we were going in that direction, we would be walking down on that surface. So your z would be decreasing. Okay. Let's look at a function in 3 variables. So find the directional derivative of f of x, y, z, which is equal to x, y, z, at the point 2, 1, 1. In the direction of u is equal to 2, 1, 2. That's your vector. The directional derivative of f in the direction of u is going to be the partial of f with respect to x times a plus the partial of f with respect to y times b plus the partial of f with respect to z times c, where a, b, and c are the I, j, and k components of the unit vector respectively. Okay, so we do need a unit vector. So in order to do the directional derivative, the vector needs to be a unit vector. So we're going to go ahead and take our vector and divide it by its magnitude. And this is going to make sure that we do have a unit vector. So it's going to be 2, 1, 2 all over 3. Hang on a second. Oh, we're fine. Sorry, I was looking at the point 2, 1, 1. I was like, oh, we're in trouble with that. No, the vector is 2, 1, 2. So we're good. All right. So vector A is going to be, or the I component. The I component, A is 2/3. The J component is going to be 1/3, and the K component is going to be 2/3. Partial of f with respect to x is yz. Partial of f with respect to y is going to be xz. And the partial with respect to z is going to be xy. So the directional derivative of f in the direction of u is going to be 2/3 yz plus 1/3 xz plus 2/3 xy. And then we want to calculate the directional derivative in the direction of u from the point 2, 1, 1. Okay, so that's going to give us 2/3 plus 2/3 plus 4/3, or it's going to be 8/3. So we can interpret this as going up in 4 dimensions, because this is a function of 3 variables. So the output would be like a w or something, so it would be 4 dimensions. Okay, we're going to go ahead and change gears, and we're going to be looking at the definition of a gradient of 2 functions. Okay, so the definition of gradient of a function of 2 variables: let z equal f of xy be a function of variables x and y, such that the partial of f with respect to x and the partial with respect to y of f exist. Then the gradient of f, so we have the upside down triangle, so like delta but flipped over. So the gradient of f of xy is the vector. So the gradient of f of xy is going to be a partial of f with respect to xi plus the partial with respect to y, the partial of f with respect to y, xyj. The gradient is a vector. Okay, so be careful. Directional derivative is not a vector, but the gradient is a vector. The gradient of f is read del f gradient or gradient. I usually refer to it as the gradient of f. And the upside down triangle here is nabla. Okay, we have a theorem for the alternative form of the directional derivative. If f is a differentiable function of x and y, then the directional derivative of f in the direction of the unit vector u is, so the directional derivative of f of xy in the direction of u is going to be equal to the gradient of f of xy. The gradient of f of xy is a vector dot product with the unit vector. So you got a dot product of two vectors, which produces a scalar, so that looks good. Okay, some properties of the gradient. If the gradient is equal to 0, this implies that the directional derivative of f of xy in the direction of u is always equal to 0 for any direction you choose, any unit vector. Okay, dot product with the 0 vector is going to be 0. Okay, and then the second item, if the gradient of f of xy is not equal to 0, then the direction of max increase, the steepest ascent of f, is the gradient. So it's going to tell us the direction of greatest ascent. The maximum value of the directional derivative is going to be the gradient. It's going to be the magnitude of the gradient of f of xy. Okay, the third thing that we have about the gradient is the gradient is not equal to 0, then the direction of minimum increase of f is going to be negative of the gradient. A sketch of the proof for item 2. Recall that the dot product of vectors a and b in the alternative form is going to be the dot product of a and b is equal to the magnitude of a times the magnitude of b times the cosine of phi, where phi is the angle between the vectors. So for the vector's gradient of f at x naught, y naught, and u, the directional derivative of f of x naught, y naught in the direction of u is equal to the gradient of f of at x naught, y naught, dot product with the unit vector u. Okay, and so that dot product is going to be equal to the magnitude of the gradient of f at x naught, y naught times the magnitude of the unit vector u times the cosine of phi. That phi is the angle between the two vectors. This will be a maximum when the cosine of phi is equal to 1. So cosine of phi is going to be equal to 1. That's going to be when phi is equal to 0. Okay, now the unit vector has a magnitude of 1. Okay, cosine of phi is going to be 1, and so the maximum value is going to be the magnitude of the gradient of f of x naught, y naught. Okay. All right, so let's go ahead and look at the next slide here. So we have an image from the Calculus Volume 3 on page 432. So we have some sort of surface here, and we have a point on the surface. P naught is x naught, y naught, z naught. And then we have a curve. And then you see in orange, you have the gradient of f, and that's going to be the most rapid increase. And then if you go in the opposite direction of the gradient, that's going to be the most rapid decrease. Okay, and we'll look at a couple examples of finding this, and we'll see what that looks like on some surfaces. And both we'll look at their projections into the xy plane, and then we'll also look at it in 3 space. Okay, so let's look at an example here. And it says the temperature at a point on a metal plate is given by T of x comma y is equal to x over x squared plus y squared. In what direction is the greatest heat at the point -3, -1? So the direction of the greatest increase, that we're going to be looking for the gradient. What is the rate of the maximum temperature increase at -3, -1? So we're going to find the magnitude of the gradient. What is the direction of the greatest decrease at -3, -1? And so what we would be doing there is finding the negative of the gradient. And then what is the maximum temperature decrease at -3, -1? And so that'd be negative of the magnitude of the gradient at that particular point. So let's go ahead and find the gradient of T of x comma y. So we're going to do a quotient rule. So low is x squared plus y squared. D high with respect to x, so it'll be 1 minus the top function times the derivative of the low function with respect to x would be 2x. All over the low function squared. Okay. And that's your I component. Now we'll take the derivative with respect to y. So it's going to be the low function. Derivative of the top with respect to x is going to be 0, minus the top function times the derivative of the denominator with respect to y is going to be 2y, all over the denominator squared, and that's going to be your j component. Okay, so we can factor out the 1 over x squared plus y squared quantity squared, and we're going to have negative x squared plus y squared as your I component, and then minus 2xy as your j component. Okay, so part A, we're going to look at what's the direction of the greatest heat increase at -3, -1. So we're going to go ahead and evaluate at -3, -1. So it's going to be 1 over -3 squared plus 1 squared, -1 squared, excuse me, and then that quantity squared times negative and then -3 squared plus, and it should be -1 squared, but I just went ahead and said 1, and then minus 2 times -3, and then times -1. So I suppose we could say this is -1 squared. It's not going to matter. Okay. So it's going to give us 1 over 100, and then we have -8i and -6j, and we're mixing, so we don't need a comma there. Okay, and so that is going to be the direction of maximum increase. Okay, now part B is what is the maximum increase, and so we just need to find the gradient of this vector that we just found. We're missing the t here, so we're finding the gradient of t at this point. Okay, so the constant can just slide out, and then it would be -8 squared plus -6 squared, and then that is under the square root. So we have 1 over 100 times the square root of 100, which is going to be 1 over 100 times 10, and that's 0.1, and then they don't tell us what the units are, but maybe it's degrees Fahrenheit per, I don't know, inch or foot or whatever units we're doing is going to be the temperature increase. Okay. All right. Let's say this is part C. So the direction of greatest decrease is just going to be negative of the gradient, and so that's going to be 1 over 100 and then times 8i plus 6j. So no comma here. If I was using the angle brackets, then I'd use a comma there. Okay. All right. And then part D, what is the maximum temperature decrease at the point -3, -1? So that's just going to be negative of the gradient, and so we already found the gradient as 0.1, so it'd be a decrease of 0.1 degrees Fahrenheit or Celsius per whatever the unit of measurement is. Okay. Now I'm going to skip over one slide, and we're going to take a look at our temperature function. So we have the temperature at x comma y is equal to x over x squared plus y squared. So the temperature at -3 and -1 is going to be, was it -3 and -1? So -3 over -3 squared plus -1 squared. Maybe this is a different example. I think I'm doing a different point here. So let's do it at a different point here. I'm going to do a point -1, 1. So -1 over -1 squared plus 1 squared, which would be -1/2. So I think maybe this ties into my next example here. But anyways, let me talk about some stuff here. So that's my z coordinate here, and so so that's going to be my -1/2 here, and that's equal to the function. And so this is what it would look like in 2D. And then if I find the gradient, So our gradient for this particular function, so I'm doing a different point here. So our gradient for this function was t of, where was it? It was of xy was equal to 1 over x squared plus y squared, and then times, where did I have my gradient? Negative x squared plus y squared, okay, and that was the I component, and then minus 2xy, that was the j component, okay. So if we evaluate my gradient at minus 1, 1, that is going to give us 1 over, let's see, 4, okay, and then that'd be 0i, and then minus, that'd be plus 2j, okay, which would be equal to 0.5 j, okay, and so that's where this came up. That is your normal. So this is your normal line. That's the point. And so we have it right here. And so our circle is going to be something like that. And so this is going to be the direction of the maximum temperature increase, and then this would be the direction, and then the opposite direction would be the direction of minimum increase. Okay, so it looks like I changed my ordered pairs. So I was at -3, -1, so I changed it to -1, 1. So it's going to be something similar, just a different ordered pair there. Okay, let's go back and we'll look at the last example. Okay, so let's rewind it. Okay, so our last example is we're going to consider the curve r of t is equal to x of ti plus y of tj. The derivative of that r prime of t is equal to x prime of ti plus y prime of tj is the tangent to the path for all t in the domain of r of t. Let's let z equal f of xy be a differentiable function of x and y, and let the point AB be a point in the domain of f. Now let's let z equal f of xy be a differentiable function of x and y. Let the point A comma B be a point in the domain of f. Suppose A is equal to x of t naught and B is equal to y of t naught for some t naught in the domain of r of t. Consider the level curve f of xy is equal to k, and define g of t is equal to f of x of t, comma y of t, and by the chain rule, g prime of t is equal to the partial derivative of x, partial derivative of f with respect to x, of x of t, comma y of t, times x prime of t by the chain rule, plus the partial derivative of f with respect to y, x of t, y of t, and then times y prime of t by the chain rule. Since g of t is equal to k, it's a level curve, g prime of t is equal to 0. So the gradient of f of xy, which is a vector, dot product that with the derivative of r of t, which is x prime of t comma y prime of t, that's going to be equal to g prime of t. Okay, so that's going to be equal to 0 because g prime of t is equal to 0. So that means the gradient of f of xy and the tangent vector x prime of t comma y prime of t, their dot product is 0, so that means they're orthogonal. This gives the theorem that if f is a differentiable at a comma b and the gradient of f of ab is not 0, then the gradient of f of ab is normal to the level curve of ab. Okay, so we're going to look at this last example here. We're going to find the gradient of f of xy equals x minus y at the point 4 comma negative 1. The unit, and then we're going to find the unit normal vector to the level curve when f of xy is equal to 3, and then we'll also find the tangent line to the curve, and then we'll do a sketch of that. Okay. So we're going to make a note here that f of 4 comma negative 1 is equal to 4 minus -1 squared. So that gives us the 3, so where we had the f of xy is equal to 3. Okay. And then we'll look at getting at our normal vector. So the normal vector to the level curve at 4 comma -1 is going to be the gradient at 4 comma -1. Gradient of f at 4 comma -1. Okay, so the gradient of x comma y is going to be I minus 2yj. So the gradient of f evaluated at 4 comma -1 is going to be the vector I plus 2j. Now we want the unit normal vector, so we're going to take our gradient and we're going to divide it by the magnitude of the gradient. Magnitude of the gradient is going to be the square root of 5. Okay. So our unit normal vector is the gradient of f evaluated at evaluated at 4 -1 divided by the magnitude of the gradient evaluated at 4 comma -1. So it's going to be I plus 2j over the square root of 5. Okay. Now we're in 2 dimensions. So in 2 dimensions, if we want to find the tangent vector, it's quite easy. All we got to do is switch the I and j components and then make one of them the opposite sign. Typically in the problems they'll say make your I component positive. So we just need to switch the one I and the 2j. So the coefficients 1 and 2, so we need to switch it so it's 2 and 1, and then we need to make one of them opposite so that when we do a dot product the result is 0. Okay, so there's your tangent vector. And the tangent line is going to be 4 plus, and then we're going to get our slope from the tangent vector, so 2 over root 5t, and then -1, and then -1 over the square root of 5t. Okay, and then we'll do the same thing for the normal line, and then we'll graph this and take a look at what we got going on. So the normal line is going to be 4 plus, and then from the normal vector it's I over root 5, so 1 over root 5t, comma, -1 plus 2 over root 5 t, and that'll be our normal line. Okay, and so we're going to cruise on to the last slide here, and we'll take a look at that. Okay, so on the last slide here, in 2 dimensions, here's your level curve. There's your level curve. And our point is 4 and -1. And you can see your normal line and your tangent line. Okay. And then in 3 dimensions, you have, so what I did for the 3 dimensions is I also added in a 3. So that gives us the height of 3. And you have your tangent line and your normal line. Okay, so that's what we're finding there. Alrighty, so that is it for this video. It's on the longer side of the videos, and next week we'll be finishing. I think we're finishing up the rest of chapter 4. So we'll stay tuned till next time.